model.
Okay, thank you very much. It's a real pleasure to be here, and actually it's my first time in Providence, so a beautiful day for it. Okay, so this talk is really about the structure of matter, and in particular about the structure of the protons, neutrons, and atomic nuclei that make up the majority of the visible matter in our universe. Now, I don't have a pointer, so I'm just going to gesticulate at the screen. Okay. So, of course, our modern understanding is that the protons and neutrons inside an atomic nucleus themselves have substructure, right? So that's our nucleus. Those balls are the protons and neutrons. Here we're looking inside a proton, and it's made of more fundamental particles called quarks, held bound or glued tightly together by the strong nuclear force, manifesting as force-carrying particles called gluons. And to the best of our understanding, that's it. The quarks and gluons are fundamental particles. There are no deeper layers of structure. Thank you very much. Okay. So the quarks and the gluons and their interactions are encoded in the standard model of nuclear and particle physics. The framework was put together in the 1970s, and it includes just 17 fundamental particles. We see them here on the slide. We have the matter particles, the quarks, the leptrons, like the electron and its neutrino, their heavier cousins, force carriers for 3 of the 4 fundamental forces, so notably excluding gravity, that's described by the separate theory of general relativity. We have the photon for electromagnetism, W and Z boson for the weak nuclear force, the gluon for the strong nuclear force, and we have the Higgs boson. And the standard model brings them all together in this very beautiful, very elegant, very predictive framework described by the language of quantum field theory. In fact, the theory is so predictive that quite a number of these particles were predicted from the symmetries and structure of the theory before they were ever seen experimentally. So if we go back, 1983, I think, was the W and Z bosons, 1995, the top quark, 2000, the tau neutrino, and then in 2012, the Higgs boson was the last piece of this puzzle to be seen experimentally. So this is really an astonishing theory, astonishingly successful and predictive theory. And I want to give you just a little sort of feeling for quite how successful this is, arguably one of the best physics theories we've ever had. So here are just 2 examples. This first one, this is the magnetic moment of the electron. Now, that is how much torque an electron feels when you put it into a magnetic field. Here what I'm showing is the anomalous magnetic moment. That's just the deviation from the tree level or from the classical result. And this is the most accurately verified prediction in the history of physics. So if we have students taking quantum field theory, you'll understand what a heroic effort this theory calculation is when I say up to 5 loops, that's 12,000 Feynman diagrams, about 30 years of effort to get this agreement to 12 significant figures between theory and experiment. Okay, so beautifully predictive. And it's not just static quantities like that. It's predictive over an incredibly wide range of energy scales. So here's just one more example. I'm looking at deep inelastic scattering. So fire an electron at a proton and break the proton apart. That process is described by what are called structure functions. On the horizontal axis, we have energy, and we have a log scale, so this is 5 orders of magnitude in energy. We have experimental data points in the colors, the theory predictions in the yellow, everything's in beautiful agreement, right? So agreement between theory and experiment over many orders of magnitude in energy scale. However, we also know that despite how beautiful and predictive this theory is, it does not describe everything we observe about the universe. Just one example that we'll come back to later is dark matter. In fact, most of the matter in the universe is something entirely different. The standard model describes this little 5% sliver of the universe's energy density pi, more than 5 times as much as dark matter. It appears to interact gravitationally like matter, but it doesn't emit or absorb light, hence dark, right? And the rest is whatever's driving the accelerating expansion of the universe. Okay, so the standard model doesn't describe anything except that 5% sliver, and it's not just that, right? The neutrinos have masses in nature. We see that because they oscillate between flavors. This is a great undergraduate quantum mechanics problem, right? Mass eigenstate and flavor eigenstate don't match. You get oscillations. In the minimal standard model, they don't have mass. There's a matter-antimatter asymmetry that we don't understand. If you start with a big bang and equal amounts of matter and antimatter, and they go ahead and annihilate with only standard model interactions, we shouldn't have quite so much matter left over at the end. We don't understand that. Gravity, how does that fit in? Questions of naturalness. Why is there such a difference between the weak and the gravitational scales, right? So all of these things tell us that there is physics beyond the standard model, and we'd like to find it. Now, of course, there are many ways we search for physics beyond the standard model. Just one of those many is through what's called searches at the intensity frontier. So this is very precise experiments looking for, say, very small deviations from standard model predictions. So that includes things like looking at magnetic moments. We saw before the magnetic moment of the electron as the most accurately verified prediction in the history of physics. Well, the electron's heavier cousin, the muon, also has a magnetic moment, and there's currently an interesting tension between a community consensus theory value and experimental measurements of this quantity. There's some interesting first principles lattice QCD calculations somewhere in the middle, but this is an interesting tension on this front. This would be an example of an intensity frontier search, for maybe this is a hint of new physics. Dark matter direct detection experiments fall into this category. Bury a detector deep underground and look for interactions of dark matter with your detector, and many others. So what all of these searches for new physics have in common is that you have to understand standard model physics to do them. You need standard model backgrounds and benchmarks. If you're going to compare theory to experiment, you need the theory, right, to do the comparison to find the new physics. So that's really motivating this effort to understand the structure of matter from first principles from the standard model. It's firstly for its own sake, and this is one of my big motivators too, is can we really go from this beautiful, elegant, symmetric physics theory, 17 fundamental particles, to understand all of the complexities of nuclear physics? Nuclear reactions, neutron stars, all from the underlying theory. How can we see that emerge, right? But secondly, we know there is physics beyond it, but we need to understand the standard model precisely quantitatively to constrain that physics beyond the standard model and find it, right? So that's also the structure of this talk. After a little bit more introduction, I'll give you some examples from recent work in the last few years in both of these categories. And then at the end, I'll circle back around and tell you about how advances in supercomputing and algorithms are feeding back into this circle, this drive to understand the structure of matter from first principles. Okay, so if we're going to talk about the structure of protons, neutrons, and atomic nuclei from the standard model, we have to talk about quantum chromodynamics, that's QCD, that's the strong interaction part of the standard model. The strong interactions are responsible for binding the quarks and gluons into protons and neutrons, and binding the protons and neutrons into nuclei. So of course it's critical if we're going to talk about the structure of those protons, neutrons, and nuclei. However, the strong interactions are also difficult to study, particularly at low energy regions. So the reason for that is that the theory is non-perturbative. So that's what we're seeing here. This is the coupling strength of the theory, and this is the energy scale on the horizontal axis. You can see that at high energies, the coupling is small, and what that means is that a perturbative approach works. You can do an expansion in powers of that coupling. You know that squaring a small number makes it even smaller, right? Cubing it makes it smaller again. So you can do this expansion in powers of the coupling, and you can make predictions from the theory. As we go to low energies, moving to the left, and really even further to the left than this plot showing, that coupling becomes large. You can't do that sort of a perturbative expansion anymore. Why do we care about low energies? Well, that's what would be relevant to, say, the structure of a nucleus sitting at rest in your detector waiting for dark matter to hit, right? Okay, so what we're left with is a numerical approach. So the approach is called lattice QCD, and it's really exactly what it sounds like. You discretize the theory of QCD onto a four-dimensional space-time grid or lattice in such a way that you can solve the equations of QCD numerically, right? So what that looks like, formally, we have a quantum field theory, you have a path integral. What it really means practically is your discretized version of the path integral is just a really, really high-dimensional integral that you have to solve numerically. By really, really high-dimensional, I mean something like 10 to the 12 dimensions for state-of-the-art calculations, right? So this is a massive computational challenge, doing 10 to the 12 dimensional integrals. How do you evaluate them? You can't do Monte Carlo sampling naively in 10 to the 12 dimensions. It just won't work. So you do something called importance sampling, and the underlying idea is that you sample the more important contributions correspondingly more, and the less important contributions correspondingly less. And why should there be more and less important contributions? You can sort of get a feeling for it just from quantum mechanics. You know that paths near the classical path are dominant and others are less important, and you get the same sort of thing happening in the quantum field theory. Okay, so to be just a little bit more formal, we put our theory onto a space-time grid, and that means we have some finite lattice spacing and some finite lattice volume. And so, of course, you have to do the calculation over and over again with smaller and smaller spacings, bigger and bigger volumes to extrapolate to the continuum infinite volume theory. Sometimes it's also convenient to use larger than physical values of the quark masses, and I'll show you some results with larger than physical values of the quark masses later. That's really just for computational expediency, especially when we're doing things that are just at the very edge of what's possible computationally. This is a convenient trick to make the calculations more efficient. You make the quarks heavier and extrapolate down. Formally, why that's easier is in solving the equations, you have to invert matrices that get closer and closer to being singular as the quark mass gets lighter, as you invert propagators, essentially. The propagators have a mass in the bottom, right? So that's why it's more efficient. So if we just put it very concretely, this is my quantum field theory path integral, integrals over quark and gluon degrees of freedom. This is some operator I want to calculate an expectation value of. This is the exponent of the action. The action is encoding the quark and gluon dynamics of the theory. There's no I because we're in a Euclidean spacetime. If you sample contributions to this integral with this exponential weighting already built in, that's the important sampling part, then calculating the expectation value of your operator just looks like taking means and standard deviations over calculated on each of those sets of samples of the field. So that's the underlying idea. Okay. So what I really want to emphasize here is that the free parameters in lattice QCD are the same free parameters as in QCD. Right? Once you fix them, you have to use some experimentally measured inputs to fix them, right? Free parameters have to be fixed. Once you've done that, everything else is a prediction of the theory. So there is no sense in which if you calculate something about a nucleus, you're saying it's a collection of protons and neutrons. Protons and neutrons aren't fundamental objects in my quantum field theory. They don't even appear. You have quarks and gluons and the dynamics of QCD, and everything you compute all the way from the structure of the proton through to a nuclear reaction is a prediction of QCD itself. Right. Okay, I've already mentioned this is extraordinarily computationally expensive, so of course we use the world's largest supercomputers. Just to give you a sense of scale, some of the calculations I'll show you would have taken, say, 50,000 years on this laptop. It's a fairly recent model. These large computers, if everyone on Earth did one floating point operation every second for a year, that's less than one of these computers can do in 1 second. So we're talking really sort of extreme scale computation. And yet it works. So we are in an era of really high precision lattice QCD for at least simple aspects of the structure of, say, protons and neutrons. This is really in the last few years. So this is from about 10 years ago now. This is the start of that precision era of lattice QCD that we're now in. Just a couple of examples. This is the proton-neutron mass difference. Now, you can measure that very precisely experimentally, right? But what you can get from a theory calculation is an understanding of where that comes from as the very precise cancellation of the strong force pushing it one way, the electromagnetic interactions pushing it the other way to give you a cancellation that reproduces exactly, the yellow band is experiment, what you measure in nature. Right? We can see where this comes from. And of course, this mass difference is absolutely crucial, right, to life as we know it. If the nucleus of the hydrogen could decay, life as we know it wouldn't be life as we know it. Stars wouldn't have lived for more than some time after their formation. Okay, the second figure here is just another example of this. This is a heavy hadron spectrum. So these are particles like the proton, but with some heavier quarks inside. The blue points are lattice QCD calculations. The red bands are experimental measurements. This one I photoshopped on after. So that was a very nice example. This was a prediction from a lattice QCD calculation. The LHC-B experiment then knew where to look to go find the state and found it precisely where it was predicted. So we're in an era of great complementarity between theory and experiment, as you see from both of these examples, and really high precision controlled predictions. Okay, so that was 10 years ago. Let me turn to now and give you just a couple of examples. Of course, they're biased from my own work in each of these two categories. Okay, so I had to pick something for this talk. I couldn't talk about everything, so I decided to focus on the quark and gluon structure of the proton and nuclei in its sort of most elemental form. How is the proton made of quarks and gluons? So the first question you can ask is, what about the simplest properties of the proton? Its quantum numbers, its mass, its spin, its angular momentum. How do they come about from the quark and gluon constituents? Questions like this we can answer very, very precisely now. So this is the momentum of the proton, and this is a calculation showing exactly what fraction comes from up quarks, down quarks, strange quarks, charm quarks, gluons. You add it all up and you get 100%, as of course you should if your calculation is well controlled. We can answer these questions precisely. But let's go a little deeper. What about the three-dimensional distribution of quarks and gluons inside a proton? So this is described by quantities with names like form factors or structure functions, I'm going to talk about one in particular, which is called the pressure distribution of the proton. And in that story, I want to really emphasize that there's some very basic and even qualitative questions about the proton structure that we're only just beginning to answer in the last couple of years. One of those is related to the proton size, and in fact, the gluon radius of the proton. Okay, what do I mean? When you normally talk about the proton's radius, what you look up in, say, the particle data group is its charge radius. That's the radius of the proton as seen by an electromagnetic probe. Gluons don't couple directly to an electromagnetic probe. So in a very real sense, that's really a quark radius of the proton. So what about the gluon radius of the proton? Okay, let's turn to models for intuition. You start to get different answers. Let's go to an MIT bag model. This is something I studied in my undergraduate days. The gluons expand to fill the bag. And if in this model you go and do a calculation, you predict that the gluon radius should be larger than a quark radius. A constituent quark model. Basically, the gluons hide inside massive quarks, right? You would say, okay, the gluons and the quarks are co-located. Gluon radius should be the same as a quark radius. If you really like flux tubes and your vision is let's take quark and antiquark pairs, pull them apart, and the gluons always come between them as the flux tube, well, then you say the gluons are always between the quarks. The gluon radius should be smaller than a quark radius. Right? So models give you any intuition you like. So let's see if we can do better. So one way of defining quark and gluon radii in a sort of consistent way is via the pressure distribution of the proton. So protons are stable, right? Quarks are confined inside the proton. So if I'm going to draw the proton's pressure distribution, it has to look something like this cartoon. This is the center of the proton, and this is the radial distance out from the center. This is that radial distance squared times the proton's pressure distribution, and I'm showing this quantity because this is the thing that has to integrate to 0 for stability. So if it goes up, it has to come down, right? The integral has to be 0. It could go down first and then come up, or it could have an extra wiggle, but it has to look essentially like this, right? Just from stability. Drawing that, we can then ask some questions. We can say, okay, well, what's the pressure in the center of the proton? Is it more like a bike tire, like 10 to the 5 Pascal, or more like the interior of a neutron star, 10 to the 34? What about the radial extent? How does that compare to what we normally think of as the proton size, its charge radius? And importantly for me, what about the quark and gluon contributions, and how different is the radial extent of those? This is one way of getting at that question of a quark radius versus a gluon radius in a consistently defined way. Okay, so we've been able to answer this in just the last couple of years. So this is a story of synergy between experiment and theory that I'm really excited about because it's not very often that you get to make predictions on exactly the same time scale as first experiments happening. So what you're seeing here is now not a cartoon, this is now data. And the blue is the first experimental constraints on the pressure in the proton, but the experiment was only sensitive to the quark contributions. On the same time scale, we were able to do a first theory calculation of the gluon part. That's the green. And so neither experiment nor theory had both pieces, but by combining them, we were able to, for the first time, get a complete pressure distribution in the proton. We're able to see that the peak pressure near the center is closer to a neutron star than a bike tire. We were also able to see this green, though the red's just the total, the green seems to have a longer tail. So gluons seem to be acting to extend the radius of the proton out further. This is sort of the first hint as to the answer of this question. Of course, having one piece from theory, one piece from experiment is not ideal. You want to have everything from both theory and experiment. And that's where we've gone since then. That was 2019. So as we've progressed, we now have first complete theory calculations of every piece of the proton's pressure distribution, including up, down, strange, gluon, and so on. But there have also been first experimental constraints on the gluon piece that I just showed you. We had experiment only had quark, theory had gluon. Now we can actually compare our theory prediction with the experimental measurement that's happened since. And what you see is really very interesting. These are what are called generalized form factors. They are the underlying quantities that you can constrain that you then Fourier transform and combine in various ways to get the pressure distribution of the proton. To break it down a little bit more, this is an energy scale. If you come all the way over here to 0, this top thing called A, The zero momentum limit of that is just the momentum fraction that we saw before. This is telling you that gluons carry about half of the proton's momentum. And this d thing, the Fourier transform of this is related to the pressure distribution that we saw before, so it's the same information, it's just packaged slightly differently. The blue points are from a lattice QCD calculation, and the other colored bands, those are different analyses of the same experiment. So the experiment can't quite orthogonalize between these two quantities, so there's some model input that goes into doing the experimental analysis. And what you see is that the first principles theory results agree much better with one version of the experimental analysis than the others. And so again, synergy between theory and experiment. Okay, can we then take these results and say even more concretely, what about the pressure in the proton? What about the radius of the proton? And that's what we're seeing here. This is the radius of the proton. That point there is the charge radius, so what you normally think of as the proton's radius. The radius defined through these pressure distributions, it's similar, right? Same order of magnitude, not totally different. That's good, very intuitive. These red points are theory calculations of the quark contributions to the radius. The blue are theory calculations of the gluon contributions to the radius, and those other colored points come from those different experimental analyses that we saw on the previous slide that had some disagreement. That's why those are there. Here, that red point for what's called the mechanical radius of the proton, my student finished her thesis and put out that number about a week before that gray point came, which was the first experimental measurement of that quantity. So that was a very exciting day for her that right on her defense, she could unveil that her prediction had been confirmed. This one here, where we're waiting on an upcoming experiment for the first measurement there. So actually, no matter how you define the radius, mass radius, mechanical radius, these are different versions of defining the same thing. The gluons seem to be extending the proton's radius, is the qualitative feature that we have learned. Okay, so I said I'm interested in the proton's radius, but we're going via a pressure distribution. Pressure distribution might make you think about things like neutron stars. If you can calculate pressure in the proton, what about, say, a neutron-rich nuclei? Can we get any sort of input into understanding equation of state of neutron stars? We would love to. Studying nuclei using this approach of lattice QCD is very hard, and we are not at all in the same precision era that we are in for studies of the proton. And the reason is that you get a compounding exponential times factorial growth in computational cost as you try to study larger and larger nuclear systems, right? So remember, we're doing calculations via a sampling approach. It's essentially a Monte Carlo method to doing very large dimensional integrals. The noise, it grows exponentially with larger and larger nuclear systems. That means you have to take exponentially more samples to do the integrals. However, the work you have to do, the complexity of the calculation, grows factorially. And so you have to do factorially growing work on an exponentially growing number of samples. So that blows up very, very quickly. And so we can do light nuclei with atomic number, that's the number of protons and neutrons, less than about 5. And going beyond that will require revolutionary new techniques, which I'll come back to at the end when I talk about machine learning. Okay, nevertheless, over the last decade, with some collaborators, where the nuclear physics from lattice QCD collaboration, we've been pursuing this and trying to do nuclear physics from first principles. And I have this here just in case anyone wants to ask questions. We've sort of built up demonstrations of how we can do everything from things like double beta decay, which you're interested in if you want to know if the neutrino is its own antiparticle, through to things like proton-proton fusion, that's the nuclear action powering the sun, and more. But for today, I want to focus on, as I said, the quark and gluon structure of the proton. And when you get to nuclei, the question is, well, for years, nuclear physics models have said a proton looks like a collection, a nucleus looks like a collection of protons and neutrons. We know from QCD a nucleus is a collection of quark and gluons, just like a proton is. So how different is its structure from the model that it is a collection of protons and neutrons? And that's a question we can try to answer numerically through calculations. So this difference between a nucleus being a collection of protons and neutrons versus a collection of quarks and gluons is encoded in quantities with names like EMC effects and exotic glue. To give you an example here, remember at the start of the talk we talked about deep inelastic scattering, fire an electron at a proton that breaks the proton apart? Here we're looking at the deep inelastic scattering cross-section ratio per nucleon for two different nuclei, iron compared to deuterium. On the horizontal axis is the momentum of the struck quark or gluon. And what you should see from this is that this is not 1. right? This is called the EMC effect. It's named after the European muon collaboration who saw this for the first time in 1983. And what it tells you is that deep inelastic scattering off a nucleus does not look like deep inelastic scattering off the collection of protons and neutrons that makes up that nucleus, right? There is nuclear structure. So we'd love to be able to understand that from first principles, and I can show you the very first step towards doing that. So let's go back to one of the simplest things, the momentum fraction, right? Like I said, for the proton, we can very precisely say the fraction of its momentum carried by quarks and gluons. For nuclei, we can make the first step. This is the up minus down quark combination and the up plus down quark combination of the ratio of the momentum in helium-3 to that in the proton, right? The blue ellipse is the constraint from experiment, and the red band, so just on this up minus down quark combination, is the very first calculation of this type from lattice QCD, and you can see it's about 1 standard deviation away from 1. That doesn't sound super exciting. We're not resolving a difference in the structure of helium-3 to the proton. However, it's actually better than experiment could do. So if you take that one number and you include it into the global fits to lepton nuclear scattering data that are used to make these experimental constraints, you actually improve them from here to here. Even with this, which was a very first proof of principle calculation, that is hard enough to get experimentally that you can already make improvements on our experimental understanding. Okay, we are very excited about this. Seeing something that looks like not a signal is maybe not the most exciting thing, so let me show you something that is a signal. And this is what's called a signal for what's called exotic glue. Now, exotic glue is the name given to gluon contributions to the structure of a nucleus that do not come from the individual protons or neutrons. So an exotic glue operator here would vanish in a proton, but not necessarily vanish in a nuclear state. What I want you to picture is when we draw a nucleus, we normally draw it like this, right? All those yellow things, those are gluons, and we normally draw them tucked inside the balls that are the protons and neutrons. Exotic glue is explicitly not that. It's gluon contributions to the binding of the nucleus, not to the protons and neutrons that make up the nucleus in your models. And here is a first lattice QCD calculation of exotic glue. Now, I'm not showing any numbers on the axes on purpose because this is not a controlled calculation. This is where I get to play experimentalist. So we went all the way from precision lattice calculations. Now we're doing like the very edges of what's possible where the question is binary. Is there a signal for this or not? And this is raw lattice data. What a signal looks like is a bump to the left of the red point with a very precise shape, that's this curvy shape, and 0 afterwards. And we can really ask the question, can I rule out the hypothesis of no signal? And statistically, yes, I can rule out the hypothesis of no signal to better than 1 part in 10 to the 12. And so we have definitive evidence that this exists. The numbers, however, there is not control of systematics here. So I'm not going to quote numbers for the side of this effect. However, we can confirm that it exists. So this is now the impetus for a letter of intent to go and try and measure this experimentally in an ammonia target at Jefferson Lab. This was proposed by one of my colleagues, Bob Jaffe, before I was born. Okay, so those were some examples of understanding the structure of matter sort of for its own sake, to see where all the complexity comes from and compare theory to experiment. But also, of course, this is important because we know there's physics beyond the standard model. And let me give you just one example in dark matter. So, of course, there's abundant evidence for dark matter. I'm not going to go into great length, but everything from galactic rotation curves. So here's a nice spiral arm galaxy. This is moving out along a radial arm. These are the measurements we can make from visible matter, say from starlight, from the 21 centimeter hydrogen line, of how fast it's rotating. This is how fast it should be rotating. Everything's rotating too fast. It should be flying away unless there's something else acting gravitationally to keep it in, right? This is the bullet cluster, great false color picture where you're able to see clusters of galaxies collide. In pink is the luminous matter that you can see. In blue is the matter that you can infer is there through gravitational lensing. And the interpretation is, of course, that these clusters of galaxies collide, the regular matter collides and gets stuck in the middle, and the dark matter passes through, and you get this beautiful separation. There have been many more examples of this. This is the Coma cluster, large cluster of galaxies near Earth, and as far back as the 70s, it was observed that something is acting to hold that together gravitationally that we can't see, is not consistent with the luminous matter. So dark matter is our best theory describing these observations, but what is it? And there are, of course, many, many hypotheses for what it could be. Additional particles, supersymmetry, a whole big space that we'd like to constrain. Just one of many, many ways we try to constrain this space of possibilities is through what's called direct detection experiments, where we search for, again, just one example would be weakly interacting massive particles, so particles that might interact, dark matter particles that might interact with regular matter through the weak interaction, right? And one way of looking for them is to bury a detector deep underground and look for dark matter to hit, right? The detection rate depends on the properties of the dark matter. That's what we want to constrain. But also the interactions with the nucleus that you use in your detector. Because, of course, we build these detectors out of nuclei. That's what we can assemble en masse in large detectors, right? Typically also very large nuclei, things like xenon. Of course, we haven't seen dark matter in these experiments. So what you get out is exclusion plots. So this is the mass of a weakly interacting massive particle. This is, SI just means spin independent. Spin independent, dark matter, nucleon cross-section. Each experiment gets a line, and it's ruling out the phase space above its line, right? Now, what you see there in gold is what I want you to notice about this. These limits are presented as limits on the interaction of dark matter with a nucleon. That's a proton or neutron. The experiments use, say, xenon. That's 140-something protons and neutrons. So there's been a translation implicitly between not seeing dark matter hit xenon, and what that means for the property we really care about is how strongly dark matter interacts with a single proton or neutron. So how do you do that translation? It needs nuclear physics. The simplest thing is you say, do the Born approximation. Dark matter hits a single proton or neutron in a nucleus at a time. So if I know dark matter interacting with a single proton or neutron, I multiply by the number of protons and neutrons, and there's my interaction. Now, I told you, for a single proton or neutron, we're in a precision era of lattice QCD. You tell me what your theory of dark matter is, I calculate this, no problem, right? But what if it's not that simple? What if dark matter interacts with multiple protons or neutrons in a nucleus at a time? So you have additional terms here. Well, that's much harder to calculate. You also can't measure it experimentally. You'd want to do dark matter scattering to measure it experimentally, right? So how does that factor in? And so we have results that actually show that there are unexpectedly large nuclear effects in one particular quantity most relevant to dark matter direct detection experiments. So, of course, the microscopic theory of dark matter is unknown. But the generic low energy limit of a spin-independent interaction is scalar, and so what are called the scalar matrix elements are particularly relevant to a large class of possible dark matter candidates. So what I'm showing you here is these scalar nuclear effects in the scalar matrix elements compared to weak interaction matrix elements. Why am I using weak interaction matrix elements? Because that's one where we can go and measure the nuclear effects for different size nuclei, right? So this is percentage nuclear effects. This is an unphysical lattice QCD calculation. I said sometimes when you're pushing the boundaries, you make the quarks heavy. The quarks are heavy, right? In my unphysical lattice QCD calculation, I have fraction of a percent nuclear effects in helium-3 for the weak interactions. I extrapolate to the physical point. I have few percent nuclear effects, which matches precisely what you have experimentally. Experimentally, you can look at medium mass nuclei, something like tin, and you have tens of percent nuclear effects in the medium mass regime. In fact, if you then extrapolate the lattice QCD calculations further, you reproduce this also. Okay, what about the scalar matrix elements? Well, in the lattice QCD calculation, I have tens of percent nuclear effects, even in the unphysical calculation. So what does that mean for, say, xenon that's used in my dark matter direct detection experiment? Well, what it tells us is that these are unexpectedly large effects that you shouldn't neglect, but we have to do more work to see what they really are with systematic control in systems that we care about like xenon. So this is a clear sign. This was unexpected, a sign that more work is needed because this is potentially significant. Now, you notice that I said tens of percent is unexpectedly large, right? There is still a hierarchy here, and that is how you extrapolate up to larger nuclei like xenon. This is the pipeline that we're working on building. So you do have a good model of nuclei as collections of protons and neutrons. It works really very well, right? And so what that tells you is that one body effects are dominant, Two-body effects are subleading but potentially non-negligible. This couple of orders of magnitude bigger than you expect is still significant. But then you can determine one-body contributions from calculation of the proton. Very precisely, we can do that. Two-body calculations in a deuteron, three-body in helium-3, and build up systematically the different contributions, match it to a many-body theory, a model, with protons and neutrons as part of a nucleus, and extrapolate far past where you can do calculations explicitly, all the way to xenon. Right. Okay, so that's great. To do this rigorously, we need better first principles theory calculations of nuclei. And it's not just dark matter direct detection. This hits all across nuclear and particle physics. I mentioned scalar matrix elements. We need them for dark matter direct detection. But if you're interested in double beta decay, if you want to know whether the neutrino is its own antiparticle or not, the lightest nucleus that undergoes double beta decay is calcium. That's still A equals 48 protons and neutrons. If you care about the Dune long baseline neutrino experiment, so flagship experiment looking to measure the neutrino mass hierarchy and mixing parameters, they're doing neutrino scattering from argon. Argon, A equals 40. Still too big. You need the axial matrix elements of argon to do the energy reconstruction in that experiment. So these are exponentially harder problems, and even getting at them via this way of matching you still need much better precision than we're able to get with conventional algorithms. And so you ideally want exponentially improved algorithms to make this possible. So that brings me to the last little hint. So we have problems that require extreme scale computation, and extreme scale computation is still not enough when we get to nuclear physics. We also are doing first principles theoretical physics calculations that require guarantees of exactness. There are symmetries that need to be exactly respected and so on. And so putting these two things together, you get the question of, well, can I accelerate this using things like artificial intelligence and machine learning? And how do I maintain the exactness and build all of my symmetries in? Now, I want to give you just one example, just so I can give you like a little bit more of a flavor. We won't go into great detail, but a little bit more of a flavor of how you might do this. And you remember I showed you that sort of ugly equation, the most technical equation you saw, which was the matrix element of some operator, and I said you want to sample the quark and gluon configurations with the exponential of the action as the weighting. I showed you that for this because the first step of any lattice QCD calculation is you should generate samples of the quark and gluon configurations according to exponential weighting of the action, where the action describes the quark and gluon dynamics. So calculating the proton, calculating nuclei, this is the first step no matter what you're doing. Picture what that looks like as here are different samples of quark and gluon configurations. They don't look anything like this, but I'm using this. This would be a scalar field theory as an example. I want to generate these likely samples much more often than this random noise sample. This is very unlikely. These are very likely, right? That problem looks a lot like one that's seen a lot of attention in the machine learning community. If you can very efficiently write machine learning algorithms that generate these fake pictures of people's faces, and you get this much more often than you get this, surely I can use the same sort of algorithm to get this much more often than I get that, right? There's an immediate and clear parallel. There's also immediate and clear differences. So let's stack it up. My problem, I want to generate a set or ensemble of these lattice QCD gauge field configurations versus the problem of generating some set of images. Now, first, it's only this whole set of gauge field configurations that has any meaning at all. Remember I said we need them to follow a very precise probability distribution? That's a different problem than the image generation problem. Image generation, a picture of a face is a good or bad face on its own, right? I need a very precise distribution of these samples. Secondly, there's an extreme inversion of the typical data hierarchy. I have something like 10 to the 9 to 10 to the 12 numbers per sample and order thousands of samples. Images, you have, say, 3,000 numbers per sample and 60,000 samples. The numbers there aren't important. The hierarchy is what's important. You see that's an extreme inversion. That means anything that needs training data, off the table for us. That's most machine learning approaches. Long-distance correlations really drive physics, right? Picture of a face, really local structures are very important. Nose, eyes, ears, and the local structures is what's driven the development of things like convolutional neural networks. They're very efficient when you have local. We don't have local structures. We have long-distance structures, right? Different. We have symmetries that are different, complex, and have to be respected exactly. So rotations, translations with four-dimensional boundary conditions. These two configurations are identical as gauge field configurations. They look quite different as images. That's not too hard to imagine from an image perspective. Gauge transformations is harder. What these field configurations actually look like is an SU3 matrix, so a 3x3 complex matrix with unit determinant on each edge of a lattice. And a gauge transformation is a symmetry that's respected exactly that changes every single edge in a different way. So as an image, it's really hard to picture, but you're changing every single edge in a different way, and this is still identical from the physics perspective. Right? So that has to be built in. Clearly, you can't do anything using machine learning algorithms that were developed for other purposes. You have to develop this all from the ground up. Quick plug for our institute, IFI, the Institute for Artificial Intelligence and Fundamental Interactions in the Boston area, so really close to you. The entire mission of this institute is to develop machine learning tools with fundamental physics principles built in for problems like this. Okay, so I'm talking about machine learning and I want to do my theoretical physics calculations. One really critical thing is there's only one thing machine learning can do for me, and it can get me the answer faster, right? I'm doing an integral. If the answer's 2, the answer better be 2, no matter how I get it. I'm not looking for hidden structures in my data. I'm literally doing an integral, right? And so what I have to do is set up the machine learning as part of my workflow like this, such that if it is poorly trained before I even optimize anything, I get the correct results. If it's well trained after I've optimized, I get the correct results, but ideally much faster. And ideally that faster is the difference between something being possible and not being possible, right? This is, I need to have mathematical guarantees that I'm still doing a first principles theoretical physics calculation, otherwise what's the point? Okay, so there are various ways you can do this, and I want to give you like a flavor of this. The first and most boring is do the calculation the same way but faster. This is sort of, as I said, boring and uninteresting, but it can be very effective. By that I mean you use machine learning to tune the parameters of an existing algorithm. Some algorithms have a lot of knobs to tweak to make them efficient, and you can very, very efficiently use machine learning to tweak those knobs. And so you're not changing anything. You have all the guarantees of your original algorithm because you're still using it. You're just using it faster, right? To go from the same place, the start, to the same finish, which is your provably exact theoretical physics calculation. Sometimes very effective use of AI, less interesting than some of the others. Second option, transform the problem into a different problem that's computationally easier to solve with your existing algorithm. So you keep all of the guarantees of using your existing algorithm because you're still using it. But you've changed your problem into one that has the same solution, but has a much shorter path to run along. So examples of this, let's say you want to do matrix inversions, right? A naive way of using machine learning to do this is say, get a lot of matrices and the inverses, train my neural network to take in the matrix, give me the inverse. Okay, fine, but you have no guarantees at all. If you move somewhere out of your data set, you have no idea if the inverse it spits out is right or not without checking, right? Instead, exactly the same thing, but train a preconditioner, which is something you can multiply on either side of your matrix to make it easier to invert using standard algorithms, right? Put in your matrix, get out a preconditioner. When the preconditioner is good, your standard algorithm is much faster. When the preconditioner is bad, your standard algorithm still has to slog through, but you still get the right answer no matter what you do, right? You protect yourself. Another example, and this one is great, you can get a lot of mileage out of it, is changes of variables. And actually, I'm not going to talk about this, but for lattice field theory, you can do this too in this 10 to the 12 dimensional parameter space. You know when you have a complex integral and you can deform the contour however you like as long as you don't cross a pole and you have the same answer? Well, if you deform your 10 to the 12 dimensional integration contour, your field theory integration contour, in a way that you don't cross poles, you can make it much easier to solve numerically while guaranteeing that you still have the right answer, right? So you can get a lot of mileage out of ideas like that. Another is, well, solve a different problem very efficiently using AI, as long as you know how to correct it to get the exact solution back again, right? So coming back to our sampling problem, this is a very nice way of doing this, is you can solve a slightly different sampling problem as long as you have a way of reweighting or correcting or getting back to the sampling problem you're originally trying to solve in a mathematically guaranteed way. So let me give you one example of doing this for lattice field theory. You can do this using what are called flow-based generative models. The idea is basically a change of variables, right? If I can have a map that takes me from an easily sampled distribution remember we have, matrices on every edge, but just think Gaussians. Something analogous to Gaussians. Gaussians are easy to sample very quickly, right? If I have a map from something like Gaussians that takes me to the actual distribution that I want, then life's great. I take my independent samples of Gaussians, generate them very efficiently, put them through my map, and out come independent samples of the distribution I really want. Problem solved, right? The way of framing this as a machine learning problem is this is a map with many free parameters that you can optimize or learn, right, or train. Of course, if you optimize this might not be exactly your desired distribution, but as long as that map has a few very important properties, as long as it's one-to-one, as long as it has a tractable Jacobian, you can correct for any inexactnesses at the end, right? And so this is framing the sampling problem with machine learning. Now, how do you actually do that for lattice field theory? Turns out you have to start from the ground up. The very first problem is that these sort of flow-based models, they had been written down in the computer science community, but for things defined on real numbers. We have these gauge fields on each edge which live on compact connected manifolds. So the very first question is, how do you do machine learning on compact connected manifolds? The simplest example of a compact connected manifold is a circle, right? You can't just take the methods used for the real line and wrap them around. You get instabilities at the endpoints, you don't optimize correctly, you have to really start from scratch. So it turns out when we worked on this problem, it's interesting to other communities too, because of course a multi-jointed robot arm, the positions are described by angles which live on circles. So if you know how to do machine learning on things like circles and angles, it's valuable in other communities. Then you have to worry about symmetries. Now, I said we can correct for any inexactnesses at the end. That also is true for inexact symmetries. However, if you have a 10 to the 12 dimensional parameter space with a 10 to the 12 dimensional symmetry group, you can't learn that stochastically by sampling, right? So you can imagine if this is your probability density and there's a flat direction, building in that flat direction, especially when it's a very high dimensional flat direction, is much, much more efficient than trying to learn the flat direction. And so you have to design, neural network architectures that respect gauge symmetries. That's an artist's impression of how you do that. I'm not going into the details, but you can do it. And if you do that, you actually already have enough to do a very simple lattice field theory calculation and see how this works. So this is a two-dimensional U1 field theory. That means instead of my 3x3 matrix on each edge, I just have a number on the circle. So doing machine learning on circles, right? This is how you do that in a field theory context. This is, it's called the integrated autocorrelation time. It's a measure of the cost per sample. And this is changing the parameter of this theory in the direction where conventional algorithms struggle. As you can see, these are conventional sampling algorithms. You can see they get exponentially more expensive moving to the right. This is the machine learning algorithm. Based on flow models, you can see it stays fairly flat left to right. And on the right-hand side, you have orders of magnitude more efficient sampling. Okay, so this can work, toy model. What do we need to do for QCD? You have to worry about systems with complex topologies. There's a difference between in principle guarantees of exactness and in practice guarantees of exactness with a finite number of samples that you have to navigate here very carefully. Fermions. Quarks are fermions. That's unfortunate. They're anti-commuting fields. How do you deal with anti-commuting things in machine learning? You have to develop a whole new set of technology. But once you do that, here's another example. This is a field theory which has fermions in it. This is the chiral condensate. What it is exactly is not important. It's some observable that I'm measuring in the theory. And I'm using this particular example because it's one where conventional methods fail. This is the conventional sampling approach. This is the true value of this observable. This is increasing number of samples. You see, the uncertainties are going down like square root n. You think life is fine. The number's totally wrong. That's because the conventional algorithm is stuck in one sector of the topology. Imagine like a big potential barrier, and because it's an update-based algorithm, you're walking around in one sector and you never hop over the barrier, right? The machine learning approach has no updates at all. It's a direct sampling approach, and so the answer converges to the right value immediately. So what about actually scaling up for QCD? We have all the pieces, and Aurora, that is the new largest supercomputer in the world, and we just got on this year. So it was supposed to be Aurora 2019. The pandemic delayed things for quite some time, but now in 2025, we have all of the pieces of the algorithms for QCD, and we are trying to deploy them at scale for nuclear physics calculations. And this is a massive engineering challenge. We're trying to do an entirely custom machine learning framework, which is the same sort of scale as state-of-the-art machine learning algorithms used in industry applications. Right? Each sample we're generating is many terabytes, so you have to do true model parallelism across the GPU. So it's a big engineering headache to make this work at scale, and that's where we're at now. And I don't know if it's going to work at scale, right? It's an open question, but all the pieces are in place. So where are we? Well, over the last 7 years, we've put together provably-exact machine learning accelerated sampling algorithm for lattice field theory that is orders of magnitude more efficient than conventional approaches in key regions of parameter space, and it's unbiased in regions of parameter space where conventional algorithms fail. So we're deploying now, and I have great hope that this will get us a little bit past that complete glass ceiling that we have in doing nuclear physics from lattice QCD, if it works. Okay, so just to come back to the physics, why am I, I used to think of myself as a pen and paper theorist. Now I'm spending all this time developing new machine learning algorithms. It's to answer some of these questions, to overcome systematic limitations in high precision calculations, especially things like the gluon structure of the proton, things like the G-2, the anomalous magnetic moment of the muon, where there's a tension between theory and experiment. That's limited, and this can remove that limitation. Things like doing nuclear physics, which we want for things like dark matter direct detection, nuclear reactions. I want to do the whole Big Bang nuclear synthesis pathway. See if we can say something about lithium abundances, right? If we can do nuclear physics, there is so much cool science we can do. So, just to wrap up the story, we're getting new insights into proton and nuclear structure through first principles QCD calculations, from high precision controlled calculations of things like the pressure in the proton, where we have theory and experiment advancing at the same time, through to important input for searches for physics beyond the standard model. I use dark matter as an example. And there's also great excitement that new tools like machine learning could help us reach beyond the frontiers in the coming decades. So, thank you so much.
Thanks a lot, very exciting. I was wondering, there's a lot of progress with generative models of the AI in symbolic calculations in reactive physics. Yeah. For instance, people are trying to guess the master integrals from null collection. Do you think something like that could feed in the lattice QCD?
I think it could. So I gave you an explicit example of trying to accelerate sampling. However, there is another part of the calculations, which is the contraction. So you have to contract all the quarks with all the other quarks. And when you have the factorially large number of them, the order in which you do that can massively change the computational cost, because you can reuse different blocks of contractions. And that's there's some deep mathematics theory behind that, but some aspects of that are still unsolved problems where I have a lot of hope for basically being able to have code generators write very efficient sequences of contractions using things like generative AI.
More questions? I have a quick question. When you were talking about splitting up like the contributions of the quarks and the gluons of the momentum, what exactly did that do? Because I guess when I think of like a neutron, it's one soup. It's not something you can just measure the observable of, say, a particular quark versus a gluon.
Yeah, so firstly, it is a scale-dependent question. So this is the answer at some particular scale that you're probing. But what it means formally is if you write down, say, the matrix element of the energy momentum tensor, you can write down the Lorentz decomposition. You write in all possible Lorentz structures. They have a priori unknown coefficients, which are the non-perturbative objects. You can work through from what the energy momentum tensor, you have shears on the off diagonals, you have things like momentum on the diagonal, work through to what that means in terms of the coefficients of this expansion, and you can compute like that matrix element and pull out that piece, and that defines what we call a momentum fraction. Experimentally, those a priori unknown coefficients are the form factors which they constrain through scattering experiments, and you would take, say, the forward limit of that piece, like I showed you this A thing, the forward limit of that is identified as a momentum fraction.
Very nice talk. So I was wondering, you can calculate all these things analytically. Is there discussion to use them at the LHC, for instance?
Oh, yeah. There's lots of connections with LHC. So something I didn't talk about, but something I've been very excited about lately is we were able to do a first controlled calculation of what's called the Collins-Soper kernel. This is the rapidity anomalous dimension governing the evolution of transverse momentum-dependent parton distribution functions. And actually uncertainty on that is one of the important uncertainties that goes into, say, the W boson mass measurements, where there was some interesting tensions a couple of years ago. And so us being able to get a better constraint on that in the non-primitive regime feeds back into measurements like that. So you can also try to get parton distribution functions more precisely.
Depending on some measurements could be a significant source of systematic uncertainty.
Oh yeah. This is a big thing. There have been a lot of developments also in recent years. So historically, things like parton distribution functions were very difficult to constrain from lattice QCD because they're defined on the light cone and we're in Euclidean space. And so that makes life hard. So you can't actually calculate them directly. You have to come up with a clever way, which in this case is you rotate the definition off the light cone, boost to infinite momentum, and then you can do a large momentum effective theory to match back. And so that's why things like that, we were in the precision era for, say, proton structure 10 years ago, not for things like PDFs. We're just entering the era now, and so we should expect a lot more feedback into LHC physics in the coming years there too.
But you basically showed the lattice PDF, so to speak.
I showed the moment of the PDF, which can be defined through a local operator, so not a light cone quantity, and so much easier.
But at what order do you calculate? Is it leading order or next to leading order?
These are all non-perturbative calculations.
More questions? Yes.
And these advances in computation you use to address, or it's relevant to address old long-standing problems like theta QC, the strong CD without resorting to other mechanisms.
Yeah, so, I mean, there's the other axis of trying to do QCD calculations where you run into sign problems or signal to noise problems, right? Sign problems where you have an integral with lots of positive and negative contributions and they cancel, and that makes life really hard to do numerical integrals. That would be an example where you hit sign problems. This sampling problem doesn't help you there except for making it easier to brute force. However, the thing I mentioned about deforming the integration contour, you can in fact show in some lower dimensional theories we've proven that you can deform to contours that no longer have sign problems, and you can do things that were otherwise intractable. Whether that will work for QCD, I don't know, we're working on it. QCD is much harder than the low dimensional examples where we've proven it, but that is one axis where, yes, we're hoping new algorithms will open the doors.
More questions?
It's a bit of like, in the very long term, where do you think this will go? Like given the rules of QCD and QED, and you get out a simulation of like a glass of water or something? Like in the very long term, do you think there will be like an issue of macroscopic systems? Or is that really too far?
So it depends how long term I imagine. Within, like, say, my career, I don't think we're going to do ab initio of a glass of water, but what I hope is that we will ground many body methods directly in QCD, so that you do QCD calculations up to some order, maybe even up to like carbon, and that you'll use all the way up to 12 body interactions to constrain an effective field theory. You'll use that effective field theory to constrain a many body method, and so none of this will be fit. At the moment, many body methods, essentially the free parameters are fit to experimental measurements, and so ideally all of that will come from QCD directly up the pipeline, and I would love to see us get to simple chemistry. Yeah.
Sorry, the way you answered there made me think, so you have complete faith that QCD is a complete theory then? I mean, are you expecting at some point maybe to see a deviation between your calculations and what's measured experimentally all right?
Well, hopefully. I mean, that's one of the motivations, right? So things like the anomalous magnetic moment of the muon, if we can get, currently the theory value that's in tension with the experimental result, that's actually data-driven. It's using experimental input also into the theory value. And so if we can get a really precise first principles theory calculation, I mean, it would be great if that's in tension with the experiment, right? Because then that's a sign of new physics.
Do you have an inkling of where you think the QCD may fall down? Do you have a favorite for where you think you may find your first break?
No, I mean, I wish. I think if we had those, so the hints tensions, which actually I think the G-2, for example, is going away with the QCD calculation. I think no, I wish, but I think if we can start getting larger and larger systems to do these tests in, of course, small effects multiply when you get bigger systems. So I'm hoping we might see some things we weren't expecting. Yeah, but there's all the obvious places, right? We have neutrinos, we have matter-antimatter asymmetry, we have dark matter. So those are obvious places to go looking. And then you start getting into flavor physics you can do very precisely, but those tensions always seem to go away. Yeah.
Just another quick question. So you showed this pressure inside the proton,
Yeah.
and you mentioned experiment in Nature publication.
Yeah.
How exactly it was done? Is it deep elastic scattering of some kind?
That was deeply virtual competence scattering. And so that's why I said they only accessed the quark piece. What they really accessed was the charge squared weighted sum of quark contributions. That's all you can access via that method. Basically, these generalized form factors are also known as the gravitational form factors because they are what would encode graviton scattering from the proton. You can't get a graviton, so you need to use two photons to act like a graviton and give you the spin.
Right, but you still don't get gluon part. So the gluon part you then get from the lab or something?
Yeah, only indirectly.
That's why there's big uncertainty method 1 and method 2.
Question in the spirit of like a glass of water and many body methods, could you do something like use lattice QCD to come up with like good density functionals for nuclear physics and then like simulate like these large nuclei or neutron stars with TFT?
Yeah, that's sort of part of the hope of this matching process is that eventually we'll be able to do that. So some of the, we're not quite there, but some of the cool things that we've done is we've sort of used these proton pressure calculations to try to match some of the initial states in heavy ion collisions that they then use in the theory evolution and try to take those models and match them to our calculations. So all those kind of things are on the table, yeah.
Questions? Okay, if there are no more questions, let's thank you.
Thank you.